A rocky world the size of Earth is orbiting a star 120 light-years away, and the James Webb Space Telescope just caught something drifting in its sky that should not be there. An atmosphere, thick, chemical, alive with motion. You will see a planet where iron rain falls sideways, a sun that never sets on half the surface, and a single molecule that on Earth is made only by living creatures. If wonders like this pull you in, tap subscribe so you never miss one. Lights down, breathe in, prepare yourselves, we begin. It was a quiet Tuesday at the Space Telescope Science Institute in Baltimore when the data began streaming in. The target was a small rocky world circling a dim red star 120 light-years from Earth. The observation had been scheduled months earlier. Nobody expected fireworks. Most of these little planets come back dead. Bare rock, empty sky. A cold tombstone floating in the dark. This one was different. The first graph that appeared on the screen showed a curve that nobody in the room could explain. A dip in the starlight? Yes, that part was normal. But the shape of the dip, the way certain colors of light had been swallowed while others passed through untouched, that part broke the pattern. Something had filtered the star. Something between the star and the telescope. And that something was wrapped around the planet. A young astronomer leaned closer to her monitor. She zoomed in on the spectrum. The little valleys in the light were in the exact places you would expect if a thick blanket of gas were hugging the surface of that distant world. Not a thin whisper of hydrogen, not a leftover trace of helium, a real atmosphere, the kind you could stand inside if the heat did not kill you first. She called her supervisor. He asked her to run it again. She ran it again. The signal stayed. He asked her to run it a third time. Same result. By the fourth pass, the coffee in the room had gone cold, and nobody was sitting down anymore. The planet in question had a modest name, a string of letters and numbers that scientists use when they do not want to get attached. For our purposes, call it the twin. It is roughly the size of Earth. It is roughly the density of Earth. It sits in what astronomers loosely call a possibly survivable distance from its star. And now, apparently, it has something wrapped around it that our planet also has: air, or at least a close cousin of air. Here is why that Tuesday mattered. For decades, scientists have stared at rocky exoplanets the size of ours and found nothing on top of them. Naked worlds, stripped bare by radiation. The working theory was simple and a little sad. Small rocky planets around these angry little red stars should not be able to hold onto their skies. The stars flare too often. The gravity is too weak. The air blows away like smoke in a hurricane. The twin was supposed to be another naked world. It is not. Webb saw gas there. Real gas. Chemical gas. The kind that reacts with light in ways that fingerprints do with ink. And the fingerprints did not match any simple expectation. Carbon showed up. So did hints of heavier molecules. The data was loud enough that within hours, emails were flying across 3 continents. Within days, observation time was being quietly rebooked. Within weeks, a small group of scientists had agreed, off the record, that this might be the most important rocky planet observation of the decade. They have not told the public everything yet. They are running checks. They are arguing behind closed doors. But the first crack in the silence has already opened, and through that crack, a far stranger question is beginning to leak out. Because if the twin has an atmosphere, something had to be holding it there. To understand why astronomers went pale when the twin's spectrum came back, you have to understand how rare this moment actually is. For the last 30 years, humans have discovered thousands of planets orbiting other stars. Big planets, small planets, hot ones, icy ones, planets made of diamond dust, planets where it rains glass. The count keeps climbing past 5,000 and shows no sign of stopping. Every month, another dozen worlds get added to the list, but almost none of them are like us. Most of what we find out there are gas giants, swollen balls of hydrogen bigger than Jupiter, puffing around their stars so close that a year lasts only a few days. Those are easy to spot. They are loud, in a sense. They block a lot of starlight. They tug on their suns hard enough for our instruments to feel it. Finding a Jupiter is like spotting a lighthouse in fog Finding a rocky world the size of Earth is like spotting a single grain of sand on that lighthouse from across the ocean, and finding one that has managed to hold on to a real atmosphere that is something else entirely. That is spotting the sand, then noticing that the sand is breathing. For years, the rule of thumb inside the astronomy community was harsh. Rocky planets around red dwarf stars, the most common kind of star in the galaxy, were considered almost certainly airless. The reasoning was grim but simple. Red dwarfs are small and cool, so any liquid water zone around them sits very close in. Any planet in that zone gets roasted by radiation. Any atmosphere those planets start with gets torn away, molecule by molecule, over billions of years. By the time you and I show up to look at them, they should be bald rocks, dead worlds with dead skies. Scientists had already checked several of these candidates with Webb before the twin. One by one, the answers had come back the same. No atmosphere, no atmosphere, no atmosphere. A quiet parade of disappointment. Some researchers were starting to whisper that maybe the whole red dwarf zone was a dead end. That Earth-like life, if it exists at all in the galaxy, would have to cling to rare stars like our Sunday. Then the twin spoke up. One single detection, one good planet with a thick, measurable sky, and the whole argument flipped upside down, because if this one world kept its atmosphere, it means something in the recipe is different. Maybe the star is calmer than expected. Maybe the planet has a magnetic shield. Maybe there is a process, something we have not guessed yet, that protects small worlds from their angry little suns. Whatever the reason, the math of the galaxy just changed. There are roughly 200 billion red dwarf stars in our galaxy alone. If even a small fraction of them can hold an Earth-sized planet with a real atmosphere, then the number of places where something interesting could be happening becomes almost impossible to count. And that is when the unease starts. Because the twin is not just a data point anymore. It is a door. And behind that door, blowing gently through the gap, is a wind nobody expected to feel. The sun the twin orbits is nothing like ours. Our sun is a calm, middle-aged yellow star. It has bad days, sure. Solar flares flicker out now and then. But on the whole, it is steady, predictable. The kind of star you could raise children under. Earth has been basking in its warmth for 4.5 billion years, and the worst it has thrown at us has mostly bounced off our magnetic shield and our thick air. The twin got a different kind of parent. Its star is a red dwarf. Small, dim, deep red in color. The kind of star you could never see with your eyes from Earth, even if you stood right next to it in space. A red dwarf is less than half the size of our Sunday. It burns cooler. It glows weaker. In terms of pure brightness, it is almost pathetic compared to the thing that lights up our sky. Do not let that fool you. These little stars are monsters in miniature. Red dwarfs are famous for one thing above all else. They flare, constantly, violently. A single flare from one of these stars can outshine the entire rest of the star for hours. During that time, the flare spits out a blast of radiation and charged particles at the planets orbiting nearby. And because habitable worlds around a red dwarf have to huddle in close just to stay warm, they catch every one of these blasts square in the face. Imagine living next to a campfire that sometimes, with no warning, throws a 10-foot tongue of flame straight at your tent. Now imagine that campfire does this every few days, for 10 billion years. That is what the twin has been living through. Our sun, by comparison, has maybe a handful of truly violent flares each year, and even those are mild compared to what the twin star regularly produces. Some red dwarfs have been recorded throwing off flares hundreds of times stronger than anything our sun has ever done. The energy released in a single one of these events can exceed the energy in every nuclear weapon humanity has ever built, multiplied by a number that stops meaning anything after a while. These flares should have finished the twin off long ago. That is the whole point of the concern. Every time a flare hits an atmosphere, it chips away at it. Molecules get ripped apart. Light gases get accelerated until they escape the planet's gravity entirely. Over billions of years, this process is supposed to leave behind nothing. A scorched stone, a sterilized corpse. Webb looked at the twin and saw an atmosphere that should have been stripped away 1,000 times over. Something is keeping it there. Something is fighting back. The leading guess for now, is a magnetic field, a strong one, strong enough to deflect the stellar wind, strong enough to absorb the worst of the flare radiation, strong enough to hold the sky in place while the star rages overhead. Earth has a magnetic field too. Ours is generated by molten iron churning deep in our core. Whether the twin has the same thing or something stranger, nobody yet knows, but it has something. And that something is the first clue. Here is a question that sounds impossible the moment you hear it. How do you measure the air on a planet you cannot visit, cannot photograph, and cannot even see directly with the most powerful telescope ever built? You use a trick with starlight. When a planet passes in front of its star, which from our angle the twin does every handful of days, a tiny amount of the star's light has to pass through whatever is wrapped around that planet on its way to us. If there is nothing around the planet, the starlight comes through unchanged, a clean beam. But if there is an atmosphere, that atmosphere acts like a filter. Different gases drink up different colors of light. Water vapor has its favorite colors. Carbon dioxide has its own. Methane has others. Each gas leaves a signature in the leftover light, a set of missing colors that act like a barcode. Webb reads those barcodes. The telescope does not take a picture of the planet. It never sees the planet as anything more than a blip. What it does is measure the star's light before the planet crosses in front, during the crossing, and after. Then it subtracts one from the other. Whatever is left is the signature of the planet's sky. This is called transmission spectroscopy, and it is the most delicate measurement human beings have ever attempted to make with a telescope. The numbers involved are almost absurd. The amount of light being filtered by the twin's atmosphere is about 1 part in 10,000 compared to the total starlight coming in. Imagine standing on one side of a football stadium and watching a single mosquito fly across a floodlight on the other side. You have to somehow notice the tiny, tiny dimming of that light caused by the mosquito's wings. Now imagine doing that across more than 700 trillion miles of empty space. Webb does it, again and again. To catch the twin's atmosphere, the telescope stared at the star for hours, watched the planet cross, and then stared for hours more. It repeated this over multiple crossings, stacking the observations on top of each other like transparent sheets, until the faint signal buried in the noise finally rose up, clear enough to read. The barcodes it pulled out were strange. There was a dip where carbon dioxide absorbs light. That by itself is already remarkable, because carbon dioxide is heavy, and heavy gases tend to hug a planet's surface, where they are harder to see from space. Seeing it loud and clear means the atmosphere is thick enough to lift the signal high. There were hints, softer and more contested, of other gases too. Water vapor, methane, something heavier, still being argued over. Each of these is a puzzle piece. Each piece, alone, could have several explanations. But when you put them together, the shape they start to form is not the shape of a dead rock. It is the shape of a functioning world, a place with weather, a place where chemistry is happening, a place that, in some small way, is alive with motion even if it is not alive with life. And the next piece of the puzzle was the one that made scientists stop laughing in the data room. The first clear signal in the twin spectrum was carbon dioxide. On Earth, you know this gas as the stuff you exhale, the stuff plants breathe in, the stuff that traps heat in our atmosphere and keeps the planet warm enough to stand on. On the twin, finding carbon dioxide was not just interesting, it was stunning. Here is why. Carbon dioxide is a heavy molecule. It does not float to the top of an atmosphere easily. To detect it from Earth, using the tiny sliver of starlight that grazes the edge of a planet, you need the carbon dioxide to be present in large enough amounts to reach high into the sky. A thin wisp of it would vanish into the noise. Webb picked it up clearly. That means the twin has a lot of it, possibly a staggering amount, and that raises the first chill. If the twin's atmosphere is rich in carbon dioxide, the planet is probably a greenhouse. Carbon dioxide traps heat. More of it means more heat trapped. If this world started out similar to Earth, with oceans and mild weather, a runaway greenhouse effect could have boiled those oceans into the sky long ago. The water vapor would have risen, broken apart in the high atmosphere, and the hydrogen would have drifted off into space. What would be left behind is a dense, crushing, scalding atmosphere where liquid water is impossible. Scientists have seen this movie before, right next door. The name of that movie is Venus. Venus is nearly the same size as Earth. It sits in a slightly warmer orbit. Billions of years ago, it may have had oceans. Today, it has a surface hot enough to melt lead, an atmosphere 90 times denser than ours, and a sky of carbon dioxide and sulfuric acid clouds. If you dropped a human there, they would be crushed, cooked, and dissolved in about that order, in the span of seconds. The twins' first chemical fingerprint was the same fingerprint Venus wears. That was the moment the room went quiet, because up until that reading, people had been cautiously optimistic. The word Earth-like had been floating around, carefully wrapped in quotation marks. But floating around, the size was right. The star distance was roughly right. The density was right. It had been easy to picture, at least for a minute, a world with blue skies and maybe even oceans. Carbon dioxide in that quantity changed the picture. Suddenly, the imagination shifted. No more blue skies. No more gentle shores. The new mental image was of a sun-scorched rockscape under a yellow, poisonous sky, with winds so heavy they moved like rivers of lead across the ground. One detection, one single gas. And the twin went from a possible paradise to a possible hell in the time it took to read a graph. But there were more signals underneath, softer ones, trickier ones. Signals that did not quite fit the Venus story. A trace of something lighter, a hint of something stranger. A molecule or two that, if real, would mean the Venus comparison was wrong. And one of those molecules had no business being on a dead world at all. Buried in the twin spectrum, beneath the loud signature of carbon dioxide, was something else. Something much quieter. Something that, if you blinked, you would miss. A soft dip in the infrared, a faint absorption line, weak but stubborn. It showed up again and again, in the same place, across multiple observations. The position of that dip matched methane. Methane is a simple molecule. One carbon atom, 4 hydrogen atoms, bolted together in a tiny tetrahedral shape. On Earth, it is the main ingredient in natural gas. It leaks out of swamps. It burps out of cows. It seeps up from deep rock. And almost everywhere you find it in our atmosphere, you can trace it back, one way or another, to living things. Finding methane in a planet's air is not, by itself, a sign of life. Methane can also be made without biology. Volcanic eruptions spit it out. Certain hot, wet rocks release it when they meet each other underground. On icy moons like Titan and Enceladus, methane exists in large amounts for purely chemical reasons. No life required. But here is the thing. Methane is fragile. Once it is in an atmosphere, ultraviolet light from the host star breaks it apart quickly. In astronomical terms, it does not last. A planet that has methane in its air right now has to be making new methane all the time, or the gas would have vanished within a few hundred years. Something on the twin, under the twin, or in the twin, is producing methane continuously. This is where scientists start picking their words very, very carefully. One school of thought says the methane is coming from volcanoes. A rocky world with a hot, churning interior could be outgassing methane through cracks in its crust. That would explain the steady supply. The twin's surface, on this view, is a nightmare of lava plains and steaming vents, constantly belching chemicals into the sky. No life needed. Another school says the methane might be coming from deep water. If the twin has a hidden ocean beneath a thick shell of atmosphere or ice, then hot rocks meeting that ocean could generate methane in huge quantities. This is a well-known process. It happens at the bottom of our own oceans, at features called hydrothermal vents, where seawater seeps into the hot crust and reacts with the rock. The chemistry is real, the methane is real. And then there is the third school, the one that the scientists do not say out loud in press conferences, but whisper in hallways and sometimes write about in careful, hedged sentences in their papers. The third school says, what if something is breathing it out? On Earth, methane is a waste product for a huge class of single-celled organisms called methanogens. These are among the oldest forms of life on our planet, going back more than 3 billion years. They live in places without oxygen, deep in mud. deep in rock, deep in the guts of animals. They eat simple things, and they exhale methane. If life existed on the twin, and if it ran on similar chemistry, it would produce methane too. Webb cannot tell the three stories apart. Not yet, but it saw the signal, and it keeps seeing it. Now picture the twin itself, floating in the dark. It does not spin the way Earth spins. It cannot. Its star is so close, and the gravitational tug so strong, that long ago the planet's rotation got locked to its orbit. One full turn of the twin takes exactly as long as one full lap around its star. The effect is brutal and permanent. One side of the twin always faces the star, always, forever. The other side faces empty space, always, forever. There is no sunrise. There is no sunset. There is no tomorrow the way we mean it. On one half of the planet, the star hangs frozen in the sky, pinned to the same spot on the horizon, or the same point overhead, depending on where you stand. On the other half, the sky is black, scattered with stars, and the ground is colder than anything a human body could survive for even a moment. This setup is called tidal locking, and it is common for planets that orbit close to red dwarfs. Mercury almost does it in our own solar system. The moon already does it to Earth, which is why you only ever see the same face of the moon no matter how many nights you look up. On a moon, tidal locking is a curiosity. On a living world, it is a sentence. The day side of the twin is a roasting furnace. The star pours heat onto it constantly, without pause, for billions of years. The rocks there may be heated so intensely that, in some regions, they glow red. Any water that existed there once has long since boiled away and drifted to the cold side or escaped into space. If the atmosphere holds a lot of carbon dioxide, as Webb suggests, the greenhouse effect would push the dayside temperatures even higher. Lead could melt, tin could puddle, metal could drip. The night side is the opposite. No light, no warmth. Temperatures that plunge far below the coldest night ever recorded on Earth. If the atmosphere were thin, gases there would freeze right out of the sky, falling to the ground as strange snows of carbon dioxide and worse. The ground itself would be glassy with frost, hard as steel, cracked by the endless cold. Between these two extremes runs a narrow band of land, a ring that circles the planet from pole to pole, balanced between the scorch of endless day and the freeze of endless night. This ring is called the terminator. On the twin, it is the only place where the temperature is not immediately lethal. If anything lives on this planet, it lives there. In that thin strip, the star hangs forever on the horizon, neither rising nor setting, a permanent sunset or permanent sunrise, depending on how you look at it. The sky there would be stained orange and red, constantly, unchanging. Winds would roar across the terminator in one direction, carrying hot air from the day side into the cold, and colder air from the night side back toward the furnace. That wind is not gentle. Stand, if you can imagine it, on the terminator of the twin. The star is a swollen red coin sitting on the horizon. It does not move. Your shadow stretches far out ahead of you, across orange dust, and that shadow never shifts. Behind you, the sky darkens into a deep purple and then into black, stars crowding in, even though part of the sky is still lit. Ahead of you, the land glows faintly with heat. Behind you, the ground is cold enough to freeze the soles of your boots if you stand still too long. This is the only survivable place on the planet. A thin loop of terrain, maybe a few hundred miles wide, wrapping all the way around the world. Everything interesting has to happen here. Weather first. The temperature difference between the twins' dayside and nightside is enormous. Hot air rushes upward on the day side. Cold air sinks on the night side. Between them, air has to flow to balance the system, and it does this by ripping across the terminator in permanent, violent winds. On Earth, our worst hurricanes top out around 200 miles per hour. On the twin, simulations suggest winds along the terminator could reach 5,000 miles per hour in the upper atmosphere. That is faster than most bullets. Those winds would shape everything. They would carve the rock. They would scream across the sky in the same direction for millions of years, wearing the stone into grooves and ridges, all pointing the same way. The entire planet might look, from orbit, like it has been combed. The lower atmosphere would be calmer, still brutal, but slower. A world-ringing river of warm, wet air, if wet air exists there, would flow from the hotter side toward the cold, dumping its moisture as it went, possibly in the form of endless driving rain or endless driving snow, depending on which exact latitude you stand on. The rain on the twin might not be water, it might be something else entirely. Liquid carbon dioxide is possible. Droplets of sulfuric acid are possible. Nobody knows yet. Life, if it is here, would have to tolerate all of it. It would have to stay in this narrow zone forever. It could not migrate. It could not flee north or south with the seasons, because there are no seasons. It could not follow the sun, because the sun never moves. It would be pinned, evolutionary speaking, to a strip of land that looks the same today as it did 1 billion years ago. Some scientists argue this is actually good news. A stable environment means stable conditions for life to adapt to, no ice ages to survive, no shifting climates to kill off half the species every million years. A Terminator ecosystem, if one existed, could sit relatively untouched for enormous amounts of time. Other scientists argue it is a trap. The Terminator is narrow. The usable land is small. Any disaster that hits the ring hits everyone. There is nowhere to run. The twins' Terminator is the stage. The rest of the planet is theater you cannot enter. All the drama, all the chemistry, all the weather, all the possibility has to play out on this one ribbon of ground, and the winds above it scream at 5,000 miles an hour. Leave the Terminator, walk toward the star. Within a few hundred miles, you would be dead. The dayside of the twin is not just hot, it is furnace hot, rock melting hot. The star, close and red and angry, pours radiation onto this hemisphere without pause. On Earth, even our hottest deserts get a break every night. The Sahara cools off. Death Valley cools off. Heat radiates back into space during the darkness, and the ground recovers. On the twins' dayside, there is no darkness. There is no recovery. The heat just keeps coming for billions of years without a single moment of relief. Estimates of the surface temperature on the dayside vary depending on which atmosphere model you run. The low-end guesses put it at around 500 degrees Fahrenheit. That is already hotter than the inside of a pizza oven set to maximum. The high-end guesses, if the greenhouse effect from carbon dioxide is strong, push the number past 900 degrees Fahrenheit. At that point, you are in Venus territory, and lead would flow like water on the ground. Aluminum would soften, tin would puddle, rubber and plastic would not exist. Any machine humans sent down there would fail within minutes. The atmosphere above this inferno would not be the clear blue, you know. It would be thick, heavy, possibly the color of old butter or dirty copper, depending on its chemistry. The horizon would shimmer with heat distortion so strong that nothing in the distance would be clearly visible. Sound would travel strangely in such a dense atmosphere. The air would be so thick that voices, if humans were crazy enough to try to speak there, would come out deeper and closer, like shouting through syrup. And yet, despite the horror, there is something fascinating about this hemisphere. Because it is the engine, every erg of energy that drives the twins' weather, its winds, its chemistry, comes from the dayside. The star dumps its fury here. That energy has to go somewhere. It cannot build up forever. So it rises, it flows, it moves toward the cold night side in giant atmospheric currents, and in doing so, it shapes every other region of the planet. Without the dayside furnace, there would be no Terminator winds. Without the Terminator winds, the atmosphere would collapse. Gases on the night side would freeze and fall as snow and never come back, and the whole sky would slowly drain away to the dark side until the planet suffocated in reverse. The furnace keeps the twin alive, in a chemical sense. It is the heart that pumps the air. Some scientists have even speculated that, in certain narrow zones just inward of the Terminator, the dayside might host shallow oceans, not water. Water would vanish instantly, possibly oceans of molten salt, oceans of liquid sulfur, oceans of something we do not yet have the chemistry to describe accurately. These would be strange, glowing seas, shimmering under a red sun that never moves, with waves that crash in unbelievable slow motion because the local gravity and the liquid density combine to make the physics look wrong. Nobody can see this directly. Nobody has any picture of it, but the math allows it. And where the math allows something strange tends to eventually turn out to be real. The twins' wind is not wind in any sense an earthling would recognize. On our planet, the air moves because warm regions near the equator rise and cooler regions near the poles sink, and the spinning of the Earth twists this flow into the familiar pattern of trade winds, jet streams, and storm systems. The worst winds we ever see are in tornadoes and hurricanes, and even those rarely reach 300 miles per hour. On the twin, the air moves because one half of the world is an oven and the other half is a freezer, and the pressure difference between them is beyond anything Earth has ever experienced. Air is a fluid. Like water, it flows from high pressure to low pressure. On the twins' day side, heat makes the air expand and rise. On the night side, cold makes the air contract and sink. The result is a continuous, hemisphere-scale current, a river of atmosphere that flows from hot to cold at high altitude and from cold back to hot closer to the ground. Simulations of these flows, run on supercomputers by atmospheric scientists who have spent careers studying tidally locked worlds, predict something remarkable. The upper-level winds on a planet like the twin could reach speeds of 3,000 to 5,000 miles per hour, in some models even higher. These are not gusts, these are not storms. These are the steady, year-round average wind speeds at altitude. For comparison, our atmosphere's strongest jet streams average around 200 miles per hour. A commercial airliner flies at about 550 miles per hour. The fastest fighter jet on Earth tops out around Mach 3, which is a little under 2,300 miles per hour. The twins' upper winds, if the models are right, outpace every man-made machine that has ever flown. Near the surface, the winds would be slower because the ground drags on them. Still, speeds of several hundred miles per hour would be common. A wind like that would pick up sand. It would pick up small stones. Over time, it would carve the landscape into streamlined shapes that all point the same way, like dunes in a desert that never changes direction. The sky above such winds would be strange. Clouds, if they exist, would streak in parallel bands across the atmosphere, all moving in the same direction, never breaking into the swirls and eddies familiar to anyone who has watched weather satellite footage of Earth. The whole planet, from above, might look brushed. Lightning is another possibility. In a thick atmosphere driven by such violent motion, static charge would build up on an epic scale. Storms on the twin, if they formed, might produce lightning bolts thousands of miles long, arcing across the terminator like cracks in glass. A single flash could light up an entire hemisphere for a brief moment, then fade back into the gloom. All of this, and we have not yet touched the most unsettling part, because the atmosphere Webb detected is not only thick, it is thicker than it should be. Thicker than a small, rocky world around an angry red star should be able to hold. Something has kept it there. Something has defied 4 billion years of radiation and flare and stellar wind. Something has protected this sky. And whatever that something is, it is doing a job our models did not predict. Step back from the twin for a moment. Zoom out. Think about the improbability of what Webb actually saw. A rocky world about the size of Earth, orbiting a red dwarf star that has been flaring for billions of years, sitting close in, where the radiation is at its worst, and somehow still wearing an atmosphere thick enough to leave a clean fingerprint in starlight. According to most of the models scientists built over the last 20 years, this should not have happened. The physics of atmospheric loss is well understood. When a star flares, it throws out high-energy particles that slam into a planet's upper atmosphere. Those particles transfer their energy to atmospheric molecules. The molecules speed up. If they speed up enough, they reach escape velocity and fly off into space, never to return. Over time, this process bleeds a planet's sky away. The lighter the gas, the faster it goes. Hydrogen escapes first, helium next. Heavier gases like nitrogen and oxygen hang on longer, but not forever. For a small rocky planet close to a red dwarf, the loss rates calculated by the models are brutal. In most simulations, a planet like the Twin should have lost an Earth's worth of atmosphere, or more, in the first billion years, certainly within 3 or 4 billion, which is about how old the Twin is estimated to be. The math predicts a naked rock. The Twin is not naked. This mismatch between prediction and observation is, scientifically, a gift. It means one of the assumptions in the model is wrong. Something real and physical is happening that the theorists did not include. Finding out what that something is will rewrite the chapter on planetary habitability that textbooks have used for decades. Several candidate explanations are already being debated. The first is the magnetic shield idea. If the Twin has an unusually strong magnetic field, it could deflect most of the charged particles from the star's flares before those particles ever reach the atmosphere. Earth's magnetic field does exactly this. It bends the solar wind around our planet and keeps our sky safe. If the Twin has a field 10 or 20 times stronger than ours, it could survive flare activity that would strip a less protected planet. The second is the resupply idea. Maybe the Twin loses atmosphere steadily, but gains it back from volcanic outgassing. Active volcanoes, of which the Twin could have many given its hot interior, pump gases into the sky faster than they escape. The atmosphere would then be a balance between loss at the top and gain at the bottom, and as long as the volcanoes keep erupting, the sky stays thick. The third is the strangest. Some researchers have floated the idea that the atmosphere is thicker than expected because the planet is still young, cosmically speaking, and has not yet had time to lose its full share. This is unlikely given the estimated age of the star, but it cannot be completely ruled out. A fourth possibility, barely spoken, is that life itself is maintaining the atmosphere. On Earth, biology continuously renews the oxygen and nitrogen in our air. Without plants and microbes, our sky would slowly change composition over millions of years. If something living is pumping the Twin's atmosphere, then the atmosphere becomes evidence of its own source. Each of these ideas has defenders. Each has doubters. Only more observations will decide. Under the Twin's thick sky, on the Terminator, or perhaps reaching onto the twilight edge of the dayside, something might be moving. Slowly, heavily, catching the red starlight on its surface and reflecting it back in ways that make the planet look, to a telescope sensitive enough, like it is wearing a slow-shifting cloak. There might be oceans on the Twin, but they might not be oceans of water. Water, on most of the Twin, cannot exist as a liquid. On the day side, it would boil and escape. On the night side, it would freeze rock solid. Only along the Terminator, in a thin band where temperatures hover in the right range, could ordinary water stay liquid for long. And even there, it would compete with whatever else is floating in the atmosphere. If the atmosphere is rich in carbon dioxide and sulfur compounds, the rain falling onto any surface water might turn it acidic, thick, slow. But water is not the only liquid in the universe. On cold worlds, liquid methane and ethane form seas. We know this directly. Saturn's moon, Titan, has lakes of the stuff, photographed and measured by the Cassini mission years ago. Those lakes are real, and some of them are the size of Earth's Great Lakes. On hot worlds, other liquids take over. Molten salt, liquid sulfur, liquid carbon dioxide under pressure. Even, in extreme cases, molten rock, which is just lava, but on a planetary surface that never cools. Lava does not quite stop being interesting. The Twin might host any of these. It might host several. Some models suggest that a band near the inner edge of the Terminator could have shallow seas of liquid sulfur, shining yellow gold in the perpetual sunset, slowly flowing in the direction of the wind. Other models suggest a different band might hold pools of liquid carbon dioxide, kept in that state by the atmospheric pressure pressing down on them. These pools would be cold to the touch, but would fizz and evaporate instantly if the pressure dropped, turning into clouds of gas that rise and rejoin the sky. There is also a weirder possibility. In very thick atmospheres under certain chemical recipes, supercritical fluids can form. A supercritical fluid is a state of matter that is neither quite gas nor quite liquid. It has properties of both. It flows like a liquid, but expands like a gas. It can dissolve things that neither a pure gas nor a pure liquid can dissolve. On Venus, there is a layer of supercritical carbon dioxide near the surface, pressing down with tremendous weight. If the twin has similar pressures, it could have oceans of something that is neither sea nor sky, but a strange in-between substance that behaves in ways no Earthling has ever seen in person. And here is the disturbing thought. Life, in the most general definition, requires a solvent. On Earth, that solvent is water. Without something to dissolve chemicals in, the reactions that make life go cannot happen. But water is not the only possible solvent. Methane works for certain chemistries. Ammonia works for others. Liquid carbon dioxide, under the right conditions, has been proposed as a possible medium for exotic biochemistry. If the twin has any of these liquids in bulk, then it has the first ingredient for life that is not like us at all, and something strange might be swimming in it. Return to the methane. Webb's detection of methane in the twin's atmosphere is, by itself, not proof of anything dramatic, but the amount and the persistence of the signal, if it holds up to further observation, is what makes biologists nervous. Here is the math of methane on a hostile world. Ultraviolet light from the host star breaks methane apart. Each molecule has a lifetime measured in years or decades, not millennia. After 1,000 years, almost all the original methane in a planet's atmosphere would be gone unless something is constantly replacing it. On the twin, methane is apparently being replaced. Something is making new methane fast enough to keep the signal detectable. On Earth, more than 90% of atmospheric methane comes from living things. Cows, swamps, rice paddies, termites, the human gut, deep-sea microbes, they all produce it. The remaining 10% or so comes from geological processes, mostly volcanic and hydrothermal. If you remove life from the Earth, our methane signal would drop sharply within a few decades and vanish almost entirely within a century. An alien astronomer looking at our planet would see it. They would see a robust methane line sitting stubbornly in our atmosphere, coexisting with oxygen, which is chemically impossible in any long-term sense without constant replenishment. They would flag Earth as suspicious. They would say, quietly, that something on this planet is probably alive. The twin shows a methane signal. The debate is whether it looks like the Earth-style signal, a biological one, or the Titangent-style signal, a chemical one. The difference comes down to context. If methane shows up alone, it might be volcanic. If it shows up with ammonia, it might be non-biological chemistry. If it shows up with certain other molecules, it starts to look like something is breathing. One of those other molecules, if it is also present, would be nearly impossible to explain without life. Its name is dimethyl sulfide, and Webb has been hunting for it. Dimethyl sulfide is made on Earth almost exclusively by marine plankton. When those plankton die and decompose, they release this molecule into the ocean, and from there it drifts into the atmosphere. The smell you notice at the seashore, that sharp, clean, slightly briny smell, is partly dimethyl sulfide. On our planet, it is a biological signature as pure as any we know. There is no known process, chemical or geological, that produces dimethyl sulfide in meaningful amounts on a lifeless world. If Webb ever sees a clear dimethyl sulfide signal on the twin, the scientific community will have a problem. A beautiful, terrifying problem. Early readings of the twin's spectrum contain a tentative hint of something sitting at the right wavelength. It is weak. It is not confirmed. It might be noise, or an instrument artifact, or an overlap with another gas. The teams analyzing the data have been careful not to announce it, but the hint is there, and more observations are coming. If that signal ever firms up into a confident detection, the twin stops being a candidate and becomes, by the strictest measure we have, the first world outside our own where life is likely. Water, as far as we know, is the one non-negotiable ingredient for life. Every biological reaction on Earth happens in water. Every cell is mostly water. Every chemical pathway that makes a living thing run depends, at some level, on water molecules being around to dissolve, transport, and react with other molecules. When scientists look at a planet, and ask whether it could support life as we know it. The first question is always the same. Is there water there? And is it liquid? The twin spectrum hints at water vapor in the atmosphere. The signal is ambiguous. It is strong enough to be interesting. It is weak enough to leave room for doubt. Different analysis teams, working from the same data, have come to slightly different conclusions. Some say yes, some say maybe, some say probably not yet. This matters because water vapor in the atmosphere is a necessary precursor to liquid water on the ground. If the twin has no water vapor at all, there is no surface water either, and most of the life-friendly dreams for this planet collapse. If the twin has a lot of water vapor, the picture opens up. A thick, wet atmosphere might condense rain under the right temperatures. That rain might pool. Those pools might, under the narrow thermal conditions along the terminator, persist as seas or lakes. The Venus scenario is still possible. A hot, wet atmosphere with no surface liquid water, where all the water is trapped in vapor form high in the sky, is a plausible interpretation of the data. In that case, the twin would be a miserable hothouse, forever boiling in its own clouds. The Earth-like scenario is also possible. An atmosphere thick enough to create pressure-driven weather, with water vapor that condenses in the cooler terminator bands, and a surface that hosts shallow pools, or even oceans of real, liquid water. This is the version where hope lives. This is the version where life becomes plausible. A third scenario exists too, and it is the one with the most surprising implications. Some researchers have pointed to the possibility of a Haitian world. The word is a combination of hydrogen and ocean. A Haitian world has a thick, hydrogen-rich atmosphere pressing down on a global water ocean. The hydrogen keeps the greenhouse effect active, which keeps the water from freezing even at distances from the star that would normally be too cold. The ocean beneath is warm, deep, and potentially far more life-friendly than Earth itself. If the twin is Haitian, it is not Earth's twin in the traditional sense. Its surface is entirely covered in water. There is no dry land anywhere. Whatever lives there has to swim. And because the atmosphere is mostly hydrogen, the sky would not be blue, but a pale, hazy, yellow-white, and the rain would not fall the way it does on our world, but condense as massive, slow droplets that drift for miles before joining the ocean. Webb's data is not yet clear enough to pick between these scenarios, but one of them, somewhere in that range, is almost certainly the right picture. And if any of them include real liquid water, then everything changes. Earlier, the twin star was introduced as a flaring red dwarf. That image is understated. The flares from this kind of star are not gentle brightenings, they are explosions. When magnetic fields on the star's surface snap and reconnect, they release a burst of energy that, in seconds, rivals the output of thousands of our sun's largest flares combined. The burst includes ultraviolet light, X-rays, and a wave of charged particles called a coronal mass ejection, all racing outward into the star's planetary system at speeds of millions of miles per hour. When that wave hits a nearby planet, bad things happen. First, the ultraviolet radiation pounds the upper atmosphere, breaking apart molecules and heating the gas. Then the charged particles arrive, carrying enough energy to strip entire layers of air off the top of the planet, kicking gas into space. Finally, the magnetic shock of the coronal mass ejection compresses whatever magnetic field the planet has, sometimes pushing it all the way down to the surface, briefly exposing the ground to direct particle bombardment. Earth has weathered events like this, but rarely, and at much lower intensities. The 1859 Carrington event, the largest solar storm in modern history, caused telegraph systems to spark and set some of them on fire. If a similar event happened today, it would knock out satellites and damage power grids on a continent-wide scale. The twin star produces Carrington-level events, or bigger, multiple times per year, maybe multiple times per month, maybe more. How has the twin's atmosphere survived this barrage? This is the question that keeps atmospheric scientists awake. One possibility, as mentioned, is a strong magnetic shield. If the twin has a deep, hot core, generating a powerful magnetic field, that field could deflect most of the incoming particles. Earth's field does this. which is why northern lights happen at our poles instead of our equator. On the twin, the auroras would be constant, spectacular, and reach down to low latitudes. The entire terminator might glow green and purple all the time, lit by auroral displays caused by particles squeezing in around the field's edges. Another possibility is that the twin sits at a lucky geometric angle. Stellar flares are often directional, not spherical. If the twin's orbital plane happens to keep it out of the main blast zone of most flares, it could be absorbing only a fraction of the damage other planets in the same system would take. A third possibility is that the atmosphere is somehow self-healing. Thick atmospheres generate their own weather, their own chemistry, and their own mechanisms for recycling molecules. A very thick atmosphere with enough carbon and hydrogen cycling can, under the right conditions, absorb flare damage and reconstitute itself on timescales faster than the damage accumulates. There may be a fourth possibility that no one has yet thought of. That is the deeper truth of science. When the data disagrees with the theory, new physics is usually hiding somewhere in the gap. The twin is hiding new physics. That much is already clear. If the twin's atmosphere owes its survival to a magnetic shield, then somewhere inside this distant world, a dynamo is running. A planetary dynamo works like this. Deep inside a rocky planet, there is a core. In Earth's case, the outer core is made of liquid iron and nickel, extremely hot and constantly moving. As this metallic fluid churns, it generates electric currents. Those currents, in turn, generate a magnetic field. The field rises up through the mantle, through the crust, out into space, and wraps around the planet like an invisible cocoon. The strength of a planetary magnetic field depends on several factors. The size of the liquid core matters. The temperature of the core matters. The speed of rotation of the planet matters. A planet that spins fast, has a large hot liquid core, and contains plenty of iron and nickel produces a strong field. The twin is roughly Earth-sized, so its interior is probably similar in broad terms. But it rotates very slowly because it is tidally locked. One rotation takes the same time as one full orbit around its star, which might be only a few days. But for planetary dynamo purposes, a few days is essentially slow. Earth rotates once every 24 hours. A tidally locked planet with a 10-day orbit rotates at less than a tenth of Earth's speed. Slow rotation usually means weaker fields. So how, then, has the twin kept an atmosphere that a weak field should not be able to protect? One idea is that the twin's core is much larger or hotter than expected. If, during its formation, the planet absorbed more iron than a typical Earth-sized world, it could have a bigger core and therefore a stronger dynamo, despite the slow spin. Astronomers have already discovered exoplanets with unusually high densities, which imply iron-heavy compositions. The twin might be one of these. Another idea involves tidal heating. The star's gravity, constantly tugging on the planet, could be squeezing and stretching its interior, keeping the inside hotter than it would otherwise be. This extra heat could power a stronger magnetic field than a cooler planet would have. Jupiter's moon Io is constantly heated this way, and the effects on Io are dramatic. The moon is covered in volcanoes. Its surface is yellow with sulfur. The same basic physics could, in a different dose, be keeping the twin's interior churning. A third idea is a partial ocean-driven field. If the twin has a deep liquid ocean, and if that ocean is salty enough to conduct electricity, then the motion of the ocean could itself generate magnetic effect. This would not replace a core dynamo, but it could add to it, creating a hybrid shielding mechanism not seen in our solar system. Whatever the source, the shield is doing its job. Webb's data says so. The atmosphere is there. The air has not been stripped. This shield, if it exists, is the silent hero of the twin story. It stands between the planet's sky and the star's fury, invisible, tireless, and for all we know, built out of physics we have not yet fully written into our textbooks. Without it, nothing else on the twin would matter. With it, everything does. Before going further, look back toward home. Look at Venus. Venus is the closest thing our solar system has to a warning label. It is nearly the same size as Earth. it has a similar density. Billions of years ago, when the Sun was young, Venus may have had oceans of liquid water and a thin, breathable atmosphere. For a time, it might have been a second Earth. Today, it is a hell. The surface of Venus averages around 870 degrees Fahrenheit. Lead melts there. Tin melts there. The atmospheric pressure at the surface is 90 times greater than Earth's, which means standing on Venus would feel like standing nearly 3,000 feet underwater. The sky is filled with clouds of sulfuric acid. The wind at altitude moves fast enough to circle the planet in 4 days, even though the planet itself takes 243 days to rotate once. Venus is what happens when a rocky world goes wrong. The chain of events on Venus, as scientists understand it, went something like this. The young planet had water. The sun gradually brightened. The water began to evaporate faster than it could rain back down. Water vapor in the upper atmosphere was broken apart by sunlight, and the hydrogen escaped into space. Without water to pull carbon dioxide back into the rocks through the normal weathering cycle, carbon dioxide built up. The greenhouse effect grew stronger. The temperature climbed. More water evaporated. More hydrogen escaped. More carbon dioxide accumulated. The cycle fed on itself, faster and faster, until Venus crossed a point of no return. This is called a runaway greenhouse effect. It is one of the nastiest failure modes a planet can have. The twin could be undergoing the same story right now. The signs are present. A thick atmosphere, a strong carbon dioxide signal, possible water vapor trapped high up in the clouds, a host star that could drive atmospheric loss on the scale needed to tip the balance. If the twin is a Venus, then what Webb has discovered is not a second Earth. It is a second Venus, confirmed by atmosphere signature in another star system, proving that rocky worlds around red dwarfs can indeed hold atmospheres, but that those atmospheres may mostly be terrifying. And yet, there is a counter-argument. Venus and the twin are not identical. Venus orbits a stable yellow star. The twin orbits a flaring red dwarf. The atmospheric chemistry, the escape rates, the input energy are all different. What makes a runaway greenhouse on Venus might not produce the same result on the twin. The presence of a magnetic shield, if the twin has one, would also change the math. On Venus, there is no such shield, and that is one of the reasons its atmosphere has lost so much hydrogen over the eons. There is also the matter of the terminator. Venus has no terminator because it rotates, even if slowly. The twin has a permanent terminator because it is tidally locked. That narrow ring of twilight is a thermal refuge that Venus cannot offer. On the twin, even if most of the planet is a Venus-style oven or a freezer, the terminator could still host conditions mild enough for liquids, for chemistry, and possibly for life. So, the twin might be a Venus with a hidden garden running around its middle, or it might just be a Venus. The next observations will tell. Set aside the Venus scenario for a moment. Consider a different possibility, one that is wetter, stranger, in some ways even more unsettling. The twin might be entirely covered in water. This is the water world hypothesis, and it has been gaining ground among a small but serious group of researchers who have looked closely at the Webb data. The idea is simple in outline. If the twin formed farther from its star originally, in the colder outer regions of its planetary system, it could have accumulated a huge amount of ice. Later, through gravitational interactions with other planets, it could have migrated inward to its current position. As it warmed, the ice melted. The result would be a globe drowning under hundreds of miles of liquid water, with no continents, no mountains, no dry ground anywhere. This is not a fringe idea. In our own solar system, moons like Europa and Enceladus are thought to have subsurface oceans more massive than all of Earth's oceans combined, and they are tiny compared to the twin. A full Earth-sized world that started out as an ice planet and melted into a water planet could have a global ocean so deep it would compress into exotic forms near the bottom. Think about that depth. Earth's deepest ocean trench, the Mariana Trench, reaches down about 7 miles. On the twin, if the Waterworld story is right, the ocean could be 300 miles deep or more. At those depths, the pressure becomes so intense that water itself changes. It stops behaving like the familiar liquid you drink. It transforms into a strange crystalline solid called ice-7, and in even deeper regions, into something called superionic ice, a phase where the oxygen atoms freeze into a lattice, while the hydrogen atoms flow through it like liquid. A water world on the twin would, therefore, have a liquid ocean on top, a layer of exotic, high-pressure ice in the middle, and possibly a rocky core at the very bottom. Between those layers, no direct contact between water and rock would be possible. That last detail matters. On Earth, a huge amount of our planet's chemistry and much of our life's foundation comes from water meeting rock. Hydrothermal vents at the bottom of our oceans are thought by many scientists to be where life itself first began. Water seeping into hot rock carries minerals back up. Those minerals feed chemistry. That chemistry feeds life. On a water world with ice-7 sealing off the ocean from the rocky core, that connection is broken. The ocean sits alone, cut off from the minerals below, starved of the chemical energy that rocks normally provide. This is why some researchers argue that water worlds, despite their plentiful water, might actually be less friendly to life than planets with a mix of oceans and continents. But other researchers push back. They say that life, once it begins, is adaptable. Even without hydrothermal vents, a global ocean could host life powered by sunlight filtering through the upper waters, or by chemistry driven by the atmosphere above. The ocean of the twin, if it exists, would be enormous, ancient, and largely unexplored by any human instrument. Whether anything swims in it is anyone's guess. And yet, swimming is the right image. If the twin is a water world, then every inch of its surface is a sea. There is a specific flavor of water world that deserves its own chapter because the implications are almost too strange to believe. The theorists call it a Hycean world. A Hycean planet has two defining features. First, it has an ocean of liquid water covering all or most of its surface. Second, its atmosphere is dominated by hydrogen rather than nitrogen and oxygen. This combination changes everything. Hydrogen is a very efficient greenhouse gas. A thick hydrogen atmosphere traps heat beautifully, which means a Hycean planet can have warm oceans even at distances from its star where a planet with a thin Earth-style atmosphere would be frozen solid. It stretches the habitable zone outward by a huge margin. Planets that would otherwise be icy graveyards could, under a Hycean atmosphere, be temperate and wet. If the twin is Hycean, it is a fundamentally different kind of world from the one we first imagined. Not a rocky desert, not a Venus clone hothouse. A warm, shallow, endless sea beneath a pale, high sky, with clouds that drift for days and rain that falls in massive, slow-motion droplets, because the hydrogen atmosphere makes the air so thin that raindrops grow larger before they are heavy enough to fall. The sky of a Hycean world would not look like Earth's sky at all. Hydrogen atmospheres scatter light differently. Depending on what else is mixed into the air, the sky could appear pale yellow, faint orange, or a washed-out white. The star overhead would look smaller and dimmer than it really is, softened by the thick haze above. And because Hycean atmospheres are often deep, with hundreds of miles of gas between the ocean's surface and space, the sky would never quite end the way ours does. There would be no clear line between air and black space, just gradients, fading upward. The surface of a Hycean ocean would be busy with chemistry. Hydrogen in the air, dissolved in water, reacting with minerals washed in from whatever volcanic activity might poke through the seafloor. All of this creates an environment where organic molecules form readily. On Earth, the building blocks of life probably assembled in shallow tide pools and near hydrothermal vents. On a Hycean world, the entire surface of the ocean might be a slow, steady factory of such molecules, constantly producing new combinations over billions of years. Whether that chemistry has ever assembled itself into something that lives is the big question. Some scientists argue, yes, almost certainly, the conditions are too favorable, the time too long, the chemistry too rich. Others argue that Hycean worlds might be too calm, too uniform, too lacking in the environmental shocks that seem to have driven evolution on our planet. Either way, the Hycean possibility opens up a new category of habitable worlds, And the twin, based on early Webb data, fits some of the expected markers. Imagine standing on the deck of a ship on a Hycean ocean. The air is thick but breathable only if you have the right equipment. The sea stretches to the horizon in every direction, smooth and glassy because the gravity and air density conspire to produce lazy, slow waves. The sun is a small reddish coin hanging at a fixed spot on the horizon because, of course, the twin is tidally locked, and even on a water world, the Terminator rule still holds. You would never sail out of twilight. Somewhere in the stack of observations Webb has made of the twin, sitting in a region of the spectrum that takes teams of scientists weeks to analyze properly, there is a feature that no one wants to talk about yet. It is small. It is uncertain. It might be noise. It might also be dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine plankton. When phytoplankton bloom in the oceans, they release this molecule in enormous quantities. It drifts up into the atmosphere. It contributes to cloud formation. It gives the seashore its characteristic salty smell. Ships crossing certain parts of the ocean can sometimes detect distant plankton blooms just by the scent of dimethyl sulfide in the air. It is, in the truest sense, the smell of life. On Earth, there is no other significant source of dimethyl sulfide. No volcano produces it in meaningful amounts. No rock, when heated or dissolved, releases it. No non-biological chemistry operating at planetary scales is known to generate it. It is, as far as current science can tell, a signature that requires living organisms to produce. Imagine the implications if Webb confirms a clear dimethyl sulfide signal in the twin's atmosphere. Scientists have been careful. The announcement of a preliminary hint of dimethyl sulfide on another exoplanet called K2-18b earlier in this decade caused a flurry of excitement and then, after further observations, a significant debate. Some of the signal held up. Some of it was questioned. The final verdict on that world is still being argued, but the fact that the molecule can be looked for, that the question is scientifically real, has changed the nature of what Webb observations mean. The twin is being looked at with this question in mind. If the methane signal in the twin's atmosphere is accompanied by a dimethyl sulfide signal, the two together become much harder to explain without invoking biology. Methane alone has many possible sources. Dimethyl sulfide alone is suspicious, but the two together, at levels that require continuous replenishment, push the explanation toward life. There is no confirmed detection. Not yet. The current data shows a possible feature in the right wavelength region. The next observation windows are expected to either firm up that feature or make it vanish. And there is another wrinkle. Even if dimethyl sulfide is confirmed, the explanation of life is not automatic. Some researchers have pointed out that certain photochemical reactions in hydrogen-rich atmospheres might, under specific conditions, produce small amounts of this molecule without biology. This is an active area of research. The chemistry is not fully settled. But not fully settled is a scientist's way of saying unlikely but not impossible. And unlikely is very different from confirmed. If biology is the best explanation for the twin's signal, and if the signal holds up, then humanity will have done something for the first time in its history. It will have detected, from across the dark between stars, the chemical trace of something alive on another world. The implications are enormous, and the scientific community knows it. Walk into any conference where the twin is being discussed, and you will notice a pattern. Scientists talking about the atmosphere, scientists talking about the chemistry, scientists talking about possibilities, scenarios, models. Nobody saying the word life. There is a reason for this, and the reason runs deep. The history of astrobiology is littered with premature announcements. In 1996, NASA held a famous press conference claiming that a meteorite from Mars contained possible evidence of ancient microbial life. The story made headlines worldwide. Further analysis over the following years largely dismantled the claim. The features that looked like fossils turned out to have non-biological explanations. The announcement did long-term damage to the credibility of the field. More recently, the hints of phosphine in the atmosphere of Venus caused a similar wave of excitement. Phosphine, on Earth, is produced by microbes in oxygen-poor environments. Its presence in Venus's clouds seemed to many researchers like it might be evidence of life floating in the upper atmosphere of that hostile planet. Further observations and analysis, however, have called the detection itself into question. The amount of phosphine might be much smaller than first reported. Other explanations might work. The field has backed away from that claim, though the debate continues. These experiences have taught the community to be cautious. Extraordinary claims, the saying goes, require extraordinary evidence. A single detection, or even a handful of detections, of a suggestive molecule is not extraordinary evidence. It is interesting evidence. It is worth investigating. It is not proof. So when the twin's atmosphere shows methane, possible water vapor, and a hint of dimethyl sulfide, the careful response is to investigate further before drawing conclusions. That is what is happening right now. Multiple independent teams are reanalyzing the data. New observation windows are being scheduled. Calibration checks are being run. Alternative explanations are being tested rigorously. This is slow. It is frustrating to anyone who wants a headline. It is also the right way to do science. There is another reason for the silence. The psychological weight of announcing the discovery of alien life is enormous. Once that announcement is made, it cannot be unmade. The world will change. Governments will react. Religions will reinterpret. Cultures will pivot. Some people will celebrate. Some will panic. Some will refuse to believe it. Scientists who might hold such a discovery in their hands understand this. They want to be sure. They want multiple independent confirmations. They want every possible alternative explanation ruled out. Only then will they risk putting their names and their institutions behind the claim. For now, the twin is a candidate. A hot candidate, but a candidate. And the scientists studying it are, as a group, choosing their words with surgical precision. In private conversations, though, the excitement is harder to hide. Researchers who have been in this field for decades have described the twin data, in off-the-record moments, as the most interesting they have ever seen. Some have called it the best chance in a generation. A few have quietly admitted that if the follow-up observations hold up, the implications would be, in their words, historic. The silence in the press conferences is not the absence of excitement, it is the weight of it. The twin is approximately 120 light-years from Earth. That number hides an incomprehensible amount of space. 1 light-year, the distance light travels in a single year, is about 6 trillion miles. 120 light-years is 720 trillion miles. To put that in a scale a human can almost grasp. Light, the fastest thing in the universe, takes 120 years to cross from the twin to Earth. A beam of light leaving the twin's atmosphere right now, as you hear this, will not arrive at Earth until a time when most people alive today will be gone. The light Webb is actually collecting. The light that revealed the twin's atmosphere left that planet around the year 1900, give or take. That light has been traveling through empty space for over a century to reach us. And yet, 120 light-years is close. By galactic standards, it is our own backyard. Our galaxy, the Milky Way, is about 100,000 light-years across. The nearest other galaxy is more than 2 million light-years away. In the grand sweep of cosmic distance, the twin is practically next door. Even so, we will never go there. The fastest spacecraft ever built by human beings, the Parker Solar Probe, travels at roughly 430,000 miles per hour at its fastest. If it were pointed at the twin and given unlimited fuel, it would take almost 200,000 years to arrive. Humanity has not existed as a species, in anything resembling our current form, for that long. The first modern humans left Africa only around 60,000 years ago. A mission to the twin would need to last 3 times as long as our entire species' history to complete. There are theoretical propulsion systems that could, in principle, cut that time down. Nuclear pulse rockets, fusion drives, laser-pushed light sails. If one of these ever works at scale, travel times could drop to a few thousand years, but even that is longer than all of recorded human history. Pyramids would crumble, Civilizations would rise and fall. Languages would be born and die. Meanwhile, the tiny probe would still be out there in the dark, drifting toward its target, faster than light travel, so familiar from science fiction, has no known physics to support it. Warp drives and wormholes exist on paper as exotic mathematical possibilities, but no one has any idea how to build one, and every attempt so far has ended in theoretical frameworks that require impossible materials or impossible energies. So the twin is unreachable. This is, in a sense, a mercy. Whatever is on the twin cannot easily come here. Whatever lives there, if anything lives there, is isolated from us by a barrier of space and time that neither side can currently cross. Any communication would take 120 years one way, 240 years round trip. A question asked today would be answered in the year 2266 at the earliest, assuming anyone is listening on the other end. Our only contact with the twin is light, old, faint, patient light that has crossed the dark to reach us. Through that light, we can see, we can measure, we can guess, we cannot touch. Imagine standing on the twin's terminator, just inside the zone where survival might be possible for a protected human visitor. The ground under your boots is dusty, possibly reddish, possibly grey, carved by those permanent winds into long streaks that all run in the same direction. Look up. The star of the twin hangs at the horizon, where it always hangs, where it always has hung, where it always will hang. It is larger in the sky than our sun looks from Earth, because it is closer, and you orbit tight to it. It is redder, because it is a cool red dwarf. Its light is dimmer than sunlight, but not as dim as you might expect. The atmosphere amplifies what reaches the ground, scattering the red light around the sky until the whole overhead is a wash of orange, pink, and purple. It is a permanent sunset. It looks like a sunset that never finishes. The light never changes. The colors never fade. The star does not drop lower. It does not rise higher. It simply sits, and the whole sky sits with it. The only changes come from the clouds. If the twin has a water-rich atmosphere, there are clouds. They stream across the sky from the day side toward the night side, driven by the relentless winds. They are not the fluffy cumulus clouds of Earth. They are long, streaked, parallel banks of vapor, ribboned across the sky like brushstrokes. They might be tinted yellow or brown depending on what chemicals they contain. In places where the atmosphere thickens, they might form dense overcast that blots out the star entirely and turns the surface below into a dim red gloom. Shadows, if the star is visible, do not move. They lie stretched across the dust in the same direction, permanent, unchanging. Your shadow, if you stood there, would be a shape that had lived on that patch of ground the moment your feet touched it, and would remain there exactly the same as long as you did not move. In the far distance, on the bright side of the horizon, you would see a shimmer of heat rising off the land where the true dayside begins. It might ripple like a mirage on a desert highway. In the other direction, toward the night side, the ground darkens quickly. Over the horizon, the sky turns a deep indigo and then black, and somewhere in that blackness, unseen, carbon dioxide might be falling as frost. Above all of this, if the twin has a strong magnetic field and the star is currently erupting, auroras would dance across the sky, even during the day. Green sheets, purple curtains, ribbons of red that pulse and shift faster than anything else in the scene. These would be the only truly moving things in the sky. The sound of the twin would be strange too. If the atmosphere is thick, sound travels farther and carries more weight. You might hear the wind as a constant, low roar. Not a gust, not a gale, but a steady pressure note, low enough to feel in your chest. Nothing else would change. No clocks, no sunsets, no days and nights. Just this single, frozen, orange-red moment, stretching out for all of time. Human bodies are finely tuned for Earth. We evolved on a planet where surface gravity pulls us down at a specific strength. Our muscles, our bones, our hearts, our inner ears, all of them work optimally within a narrow range of gravitational pull. Take us off Earth, and things go wrong quickly. The twin's gravity depends on its mass and its size. Most estimates suggest it has a surface gravity somewhere between 1.5 and 2 times Earth's. That is not extreme. Astronauts train on centrifuges at higher levels. Some fighter pilots experience much greater forces during tight turns, but they experience those levels briefly. Minutes, at most, live on the twin, and you would experience that gravity every second of every day. Your body weight would effectively double or triple. Every step would feel like you were carrying a heavy backpack strapped across your shoulders and waist. Stairs would be exhausting. Running would be nearly impossible. Falling down would hit harder, break bones more easily, take longer to recover from. Your heart would work harder to pump blood against that extra pull. Your lungs would struggle under the weight of your own rib cage. Over weeks, the constant strain would damage joints and vertebrae. Within months, cardiovascular issues would likely become severe. A human visitor to the twin, even in an environmental suit, would probably not survive long-term residence without extensive medical intervention. Any life native to the twin, though, would be built for this gravity. It would evolve differently from us. Stronger bones, probably, shorter limbs, wider stance, more robust muscle tissue. Creatures on the twin might be squatter and more compact than creatures on Earth, because tall bodies are harder to support under higher gravity. Plants, if they exist there, would face similar pressures. A tree on the twin would not grow tall the way Earth trees do. The wood would have to be denser just to hold itself up. The branches would be shorter, the leaves might be thicker, to withstand wind pressure amplified by dense atmosphere. Flight, especially, would be restricted. On Earth, large birds, like condors and albatrosses, ride thermal currents to soar for hours. On the twin, the higher gravity combined with dense air would change the math. Small flying creatures might do well, actually, because the thicker air provides more lift. But large flying animals would have trouble. Their wings would need to be disproportionately huge to support their weight. Aquatic creatures, on the other hand, would not feel the gravity problem at all. Water supports body weight. A fish or fish analog on the twin could grow as large as, or larger than, equivalent creatures in Earth's oceans. If the twin is a water world, then the ocean life, if it exists, could potentially reach truly enormous sizes. Thinking about the twin from a biological perspective changes the shape of speculation. Life there, if it exists, is not going to look like life here. It will be shaped by the dense air, by the permanent wind, by the higher gravity, by the unmoving sun. Whatever has evolved in that environment, if anything has, is alien in every sense of the word. And the only way to ever know for certain would be to go there, which we cannot do, or to listen, which we are doing right now. Earth's sky is blue for a specific reason. Sunlight contains all the colors of the rainbow. When those colors pass through our atmosphere, the shorter wavelengths, particularly blue, get scattered by air molecules more strongly than the longer wavelengths. The blue light bounces around in every direction, reaching our eyes from all over the sky, while the other colors mostly travel straight through. Change the star, change the atmosphere, and the sky color changes with it. The twin's sky is not blue, almost certainly not. The star overhead is red. That already shifts the color palette before any atmospheric effects come in. Less blue light is being produced by the star in the first place, so less blue is available to scatter. The star's light is weighted heavily toward the red and infrared end of the spectrum. The atmosphere, if it is rich in carbon dioxide and possibly other gases, scatters light differently than Earth's nitrogen-oxygen mix. Carbon dioxide is a larger, heavier molecule. It tends to scatter less efficiently than small air molecules do. This means more of the light passes straight through and less gets bounced around into a diffuse glow. If the twin's atmosphere also contains hazes, sulfur compounds, or organic particulates, the sky color shifts further. Titan's atmosphere, for example, is orange because of photochemical hazes that form when sunlight breaks apart methane high in the air. The twin might have similar hazes. The resulting sky might range from pale orange to deep copper, depending on altitude and location. Near the star, the sky might look washed out and white-red, similar to the way an Earth sky looks near the sun on a hot day. Away from the star, the sky might deepen into dusky purple, or even black if the atmosphere is thin enough in places to let the stars show through. The clouds, wherever they exist, would color the view in their own ways. Water clouds would appear grey or white. Sulfuric acid clouds, as on Venus, would appear yellowish. Hydrocarbon clouds might be orange or brown. Methane clouds, if the temperature is cold enough for them to form, would be wispy and pale. Sunrises and sunsets, which do not happen on the twin in the traditional sense, would be replaced by the permanent twilight at the terminator. That twilight might be unlike any twilight on Earth, with colors that shift slowly only as clouds pass overhead or as volcanic dust enters the atmosphere. In the night side hemisphere, the sky would be black, but in a strange way. If the atmosphere extends that far, it would still glow faintly from residual heat and from auroral displays. The stars visible from the night side would be the same stars we see from Earth, roughly, but the constellations would be different because the twin is seeing the universe from a different angle. Looking up at the twin's night sky, if you could somehow stand there safely, you would see foreign constellations. Our sun, from that distance, would appear as an ordinary yellow-white star in what we might call the twin's version of a faint background pattern. Just another point of light in a sea of points. You would not recognize it as home unless someone pointed it out. Every planet has observation windows, times when the geometry of its orbit lines up just right for the telescope to collect the most useful data. For transiting exoplanets like the twin, these windows happen when the planet passes in front of its star from our viewpoint. Those are the moments when starlight filters through the atmosphere and gives Webb the barcode spectrum that reveals chemistry. The twin's windows are relatively frequent because its orbit is short. Every few days, there is another transit, but not every transit is equally useful. Some are shorter than others. Some happen when other astronomical priorities are competing for Webb's time. Some have less clean alignments with the instruments. The best windows, the ones where the telescope has enough time to stack hundreds of spectra on top of each other and dig deep into the noise, come along only a few times per year. Each one is precious. Each one is fought over by multiple research teams, each of whom has a slightly different question they want to ask of the twin's atmosphere. The next big window is approaching, and teams around the world are preparing for it. This window is expected to deliver data clean enough to either confirm or rule out the tentative dimethyl sulfide signal. It should also clarify the water vapor question, and, if certain mathematical models are right, it might reveal additional molecules that have so far sat just below the noise floor, waiting for enough observation time to emerge. Among those additional molecules, scientists are particularly hopeful for signs of oxygen. Oxygen is a big one. On Earth, free oxygen in the atmosphere is a direct product of photosynthesis. Before life learned to photosynthesize, Earth's atmosphere had almost no free oxygen. After life began producing it, the oxygen level climbed, slowly at first, then more rapidly. Today, oxygen makes up about 1/5 of our atmosphere. If all Earth's life vanished tomorrow, that oxygen would slowly be absorbed back into rocks and oceans over the course of millions of years. Finding oxygen on the twin would be a tremendous signal. Oxygen is reactive. It bonds with rocks, with metals, with other gases. Without a continuous source, it disappears. If the twin has significant atmospheric oxygen, something is making it. Chemistry alone can make oxygen, but only in specific situations. Certain kinds of ultraviolet radiation, hitting certain atmospheric compositions, can split water molecules and release oxygen. If that process is working on the twin, the oxygen would be accompanied by other chemical signatures that indicate the non-biological origin. But if the oxygen shows up in the wrong proportions alongside methane and dimethyl sulfide, the only known explanation on Earth is biology. So the coming observation window is being watched carefully. If it delivers what some scientists quietly hope it might deliver, the conversation about the twin will shift dramatically. Words that are being held back will start to be said aloud. Nobody wants to get ahead of the data, but nobody can entirely ignore what the data might show. Step back and consider the opposing view. There is a group of scientists who look at the same Webb data and come to a much less exciting conclusion. They argue that the twin is probably a dead world, that the atmosphere is real but boring, that the interesting signals are either noise or misinterpretation. Their case is worth hearing. First, they point out that the signal strengths involved in detecting molecules like methane and dimethyl sulfide on the twin are extremely small, close to the limits of what Webb can reliably measure. When you are working at the edge of your instrument's sensitivity, the risk of false positives goes up. Systematic errors, instrumental effects, data processing choices. All of these can create apparent signals that are not real. Second, they argue that even if methane is real, the simplest explanation is geological. The twin is likely volcanically active, given its hot interior and the probable tidal forces squeezing it. Active volcanism on a planet that size could easily produce the methane levels observed without any biological contribution whatsoever. Third, they note that the dimethyl sulfide signal, if it is real, is weak enough that alternative explanations should not be dismissed. Recent laboratory work has shown that certain hydrogen-rich atmospheres under ultraviolet radiation can, under specific conditions, produce small amounts of sulfur-containing organic molecules. These amounts might be consistent with what the Webb data is hinting at. No life needed. Fourth, the skeptics argue that the history of exoplanet biosignature claims is full of reversals. Mars meteorites, Venus phosphine, the early excitement over potentially habitable planets like Gliese 581g and Kepler 452b. In almost every case, closer examination has walked back the initial optimism. They expect the same to happen with the twin. Finally, they point to the environmental challenges: the flaring star, the tidal locking, the probable runaway greenhouse. They argue that even if some organic chemistry is happening on the twin, the conditions are so hostile that life probably could not establish itself, or if it did, could not persist long enough to produce detectable atmospheric signatures. Their view is not pessimistic for its own sake. It is cautious in the way that good science demands. They want the extraordinary evidence that any extraordinary claim requires. They have not yet seen it. The optimists and the skeptics, at the moment, are roughly balanced in their numbers. The field is divided. That division will be resolved, one way or the other, by the upcoming observations. Either the signals will firm up and become undeniable, or they will weaken and fade into the background as more data is collected. It is a good thing for science that the debate is happening. Consensus reached too quickly is often consensus reached poorly. The twin is forcing everyone to argue, to check their assumptions, to develop new tools for teasing real signals out of noisy data. Whatever the outcome, the methodology being developed for studying the twin will be used for studying dozens of other worlds in the coming years. The tools are improving, the questions are sharpening. Future planets, now only being discovered, will benefit from this hard work. But for now, the verdict on the twin itself remains open. Pause. Imagine the moment. Somewhere in the world, a press conference is being prepared. Scientists are sitting at a table, microphones in front of them, data in their hands. They have been debating for months, for years, whether the signals from the twin are real. Multiple independent teams have now confirmed. Every alternative explanation has been checked. The chemistry demands a biological source. The announcement can no longer be delayed. They step up to the microphones. Within minutes, news networks around the world carry the same headline, the same 10 words, roughly. Life has been detected on a planet around another star. What happens next? Cultures react differently. Some celebrate. Street parties erupt in certain cities. Fireworks are launched. Religious leaders issue statements. Philosophers write essays. Scientists give interviews. Governments release carefully worded reactions. Others panic. Stock markets wobble as people try to figure out whether this discovery means something economically. Conspiracy theories flourish online within hours, some claiming the news is fake, others claiming the discovery is actually much more dramatic than scientists are letting on. News cycles crowd with commentary from people who do not really understand the science, but who need to say something. A quieter reaction happens inside people individually. Children ask their parents questions. Parents struggle to answer. Every night, somewhere in the world, someone looks up at the sky differently than they did the night before. The stars are no longer just stars. The universe is no longer a room where humans are alone. It is a room with at least one other occupant. Philosophically, the discovery changes the math of existence. For as long as humans have existed, the question of whether we are alone in the universe has hung in the background of every serious conversation about meaning. Religions have different answers. Science has, until this moment, had no answer. With the twin, the answer becomes no. We are not alone, but we do not know what the neighbors are like. We do not know if they are aware of us. We do not know if they are complex or simple, whether they have anything resembling thought, whether they could ever be communicated with. Most likely, the life on the twin, if it exists, is microbial, single-celled, ancient, maybe exotic in its chemistry, maybe similar to Earth microbes, almost certainly not intelligent in any sense we would recognize. That fact, though, does not diminish the news. Single-celled life on another world is still a discovery of staggering importance. It tells us that life is not a rare accident unique to our planet. It tells us that, given the right conditions, biology happens. It tells us that our galaxy, with its hundreds of billions of stars and trillions of planets, is probably full of similar stories. Life on Mars, if it exists. Life on Europa, if it exists. Life on Enceladus, if it exists. Life in the galaxy beyond, scattered across countless other worlds, most of which we will never even detect. The universe would feel different after such an announcement, not because anything had physically changed, but because our understanding of our place in it would have rearranged itself. The silence that has hung over humanity's cosmic loneliness would finally be broken. While the public waits for an official announcement, and while the scientists argue in their papers and conferences, other groups are reportedly paying attention to the twin. Some of this is speculation, but some of it is documented in budget lines and meeting minutes that have found their way into public view. Several national space agencies have quietly increased their funding for exoplanet atmosphere research in the past 2 years. The trend started before the twin data came in, but it has accelerated since. Proposals that would previously have been rejected are now being approved. New instruments are being developed. New ground-based telescopes are being planned specifically to complement Webb's capabilities. Military research institutions, traditionally interested in anything that could have strategic implications, have reportedly shown interest as well. The concern is not that aliens are coming. The concern is that a confirmed discovery of extraterrestrial life would have social and political consequences, and those consequences are worth understanding in advance. Reports on the psychological impact of such a discovery on human populations are being updated. Some government task forces have been briefed on the status of the Webb observations. Religious institutions have begun, quietly, to prepare. The Vatican, which has a long history of engagement with astronomy and has operated an observatory for over a century, has reportedly commissioned internal studies on the theological implications of discovering extraterrestrial life. Similar quiet preparations are apparently happening in other major faith traditions. Nobody wants to be caught flat-footed if the announcement comes. Private industry is paying attention too. Several billionaire-funded research initiatives have announced new telescope projects, new exoplanet studies, new astrobiology fellowships. Money is flowing. The calculation is that whoever is best positioned when the big announcement comes will benefit enormously in prestige, if nothing else. Academic departments of biology, chemistry, and philosophy are all seeing increased enrollments in classes related to astrobiology. Young scientists are choosing their research fields with the twin in mind. The next generation of researchers who will eventually follow up on whatever Webb discovers is already being trained. This quiet build-up is one of the most remarkable aspects of the current moment. Nothing has been announced. No confirmed discovery has been made. And yet, large portions of human civilization are already preparing for the possibility that something is about to be announced. The smell of history is in the air, and people who work in fields where history matters are responding accordingly. If the announcement never comes, all of this preparation will have been for nothing, or it will have spun off useful side effects for unrelated research. No harm done. If the announcement does come, humanity will have been, to some degree, ready for it. That is perhaps the first time in history that the species has tried to prepare in advance for a scientific revelation of this scale. The twin has not said its final word yet. The observations continue. The analysis continues. The data is still being read, and behind the scenes, the world quietly waits. Here is the thought that keeps people awake after absorbing everything about the twin. If the twin exists, holding its atmosphere, showing its chemistry, possibly hosting something alive, then it is almost certainly not the only one. Our galaxy contains roughly 200 billion stars. About 3/4 of those are red dwarfs, the same kind of star the twin orbits. That means roughly 150 billion red dwarf stars in the Milky Way alone. Each of them potentially has planets. Many of those planets are rocky. Some of those rocky planets are Earth-sized. A fraction of those Earth-sized rocky planets are in the loose habitable zone around their star. Do the math, even with conservative estimates, and the number of potentially twin-like worlds in our galaxy comes out to the billions, tens of billions, possibly. One study suggested as many as 40 billion Earth-sized planets might orbit red dwarfs in our galaxy within the habitable zone. 40 billion. Of those, some will have atmospheres stripped away long ago. Some will be Venus-like hothouses. Some will be Hycean water worlds. Some will be dry deserts. Some will be frozen, and some unknown fraction, will be like the twin, thick atmosphered, potentially life-bearing, waiting to be found. And that is just our galaxy. The observable universe contains hundreds of billions of galaxies. Even if the Milky Way were somehow especially rich in habitable worlds, the total number of twin-like planets across the universe enters into territory that the human mind cannot easily grasp. Numbers beyond trillions, beyond comprehension. Most of those worlds will never be studied. Most are so far away that their light, even if they are out there, will not reach us during the lifetime of our current civilization. Most will exist forever as mathematical certainties, real in theory, forever beyond our instruments. But some, the closer ones, the ones around bright red dwarfs in our neighborhood, are accessible. Webb and its successors will keep looking. New telescopes are already being designed. The Habitable Worlds Observatory, planned for launch in the 2040s, is specifically intended to study Earth-like planets around Sun-like stars. Other missions, involving arrays of smaller telescopes linked together to act like one enormous telescope, are being drawn up on paper. In the coming decades, the list of known twin-like worlds will grow. The observations will become more detailed. The spectra will become cleaner. The chemistry of more and more atmospheres will be catalogued. The tools to answer the question, "Is this world alive?" will sharpen from blunt instruments into precision scalpels. If the twin is confirmed as a life-bearing world, the hunt will intensify. Every new candidate will be scrutinized. Every faint signal will be checked. The assumption will shift from "these planets are probably dead" to "these planets might be alive, and we need to find out." Human beings have always wanted to know whether they are alone. For most of our existence, we have had no way to find out. In the past few decades, we have developed the tools to start looking. And right now, in the past few years, those tools have started returning results that point toward an answer. Whatever that answer turns out to be, the search has already transformed us. We are no longer the species that wonders. We are the species that looks. Not everyone thinks the search is a good idea. There is a theory, popularized in a science fiction novel and taken seriously by some thinkers, called the dark forest theory. It argues that the universe is silent, despite all those potentially habitable planets, for a disturbing reason. Any civilization advanced enough to communicate across interstellar distances would also be advanced enough to be dangerous. The safest strategy, upon detecting another civilization, might be to destroy it before it destroys you. The theory suggests that smart civilizations therefore stay quiet, listening carefully, attacking preemptively, and generally treating the galaxy like a dark forest full of hunters. In this view, broadcasting our existence is foolish. Answering alien signals is foolish. Even passively revealing our chemistry through atmospheric observation could, in principle, mark us as a target. Most scientists do not take the dark forest theory very seriously. It requires a lot of assumptions about alien psychology and technology that may not hold. It assumes that predation is the default behavior of advanced civilizations, which is not obviously true. It assumes that hiding is effective, which it may not be, and it assumes that aggressive civilizations would be common, which is not certain. Still, the theory raises a question that is worth asking. When we find a world like the Twin, and when we announce its existence, what are the risks? The Twin's inhabitants, if any, are probably microbes. Microbes do not care whether we know about them. They have no way to come here. They have no way to threaten us. The risk, in that sense, is minimal, but the Twin is one world among the many we are searching. If we eventually find a more advanced civilization, the calculus changes. Sending a signal to their star, or being discovered by their equivalent of Webb, could have consequences we cannot predict. Some scientists have argued for a careful approach. Observe, but do not broadcast. Listen, but do not announce our location to the galaxy. Publish discoveries, but through channels that any hostile civilization advanced enough to pick up radio signals could already monitor anyway. Others argue the opposite. Hiding is pointless, because our radio and television signals have been leaking into space for over a century. Any civilization within 120 light-years of Earth, roughly the distance of the Twin, has probably already detected us if they were looking. The horse, so to speak, has long since left the barn. The Twin does not pose a dark forest risk by itself, but the process of discovering the Twin, and worlds like it, is forcing humanity to have conversations it has never had before, about our place in the universe, about the ethics of discovery, about the responsibilities that come with knowing more. These are new problems, not problems that our ancestors faced, not problems that have traditional answers. They are problems that will have to be solved by the generation of humans alive right now, as the tools of astronomy hand us more and more information about what is out there. The Twin is a mirror as much as a planet. Looking at it, we see not only its atmosphere, but our own reflection, and we have to decide, slowly, what kind of species we want to be in a universe that turns out to be more crowded than we thought. 31 chapters in, and one more question is worth sitting with before the end. What does the Twin mean about us? For most of human history, Earth was the universe. The sky was a dome, close and familiar. The stars were lights, nothing more. The sun and moon moved across the heavens for our benefit. Everything humans saw, they interpreted as part of a story in which humans were the main characters. Science stripped that story away slowly. Copernicus moved Earth away from the center. Galileo showed that Jupiter had its own moons, which orbited Jupiter rather than Earth. Newton showed that the same physics governed the fall of an apple and the orbit of a planet. Hubble showed that our galaxy was one of countless galaxies in a vast, expanding universe. Each discovery moved humans further from the center and reduced our cosmic importance. The Twin is the latest step in that process, and maybe the sharpest one yet. If the Twin has life, then Earth's life is not unique. What happened here happened there. Whatever we thought was special about our planet may turn out to be common. The origin of life, which has felt for centuries like a near-miraculous accident, becomes something closer to a chemical inevitability when the right conditions are met. That is a humbling thought. It means Earth is not the cradle. Earth is a cradle, one of many, possibly a very ordinary one. It also means that the thing that feels most remarkable about us, the fact that we exist at all, is less remarkable than we believed. Life in the universe is not a miracle, it is a consequence. Given time, given water, given chemistry, given a reasonable climate, life simply happens, everywhere it can. This could be depressing. It reduces our importance. It takes away our claim to uniqueness. It could also be comforting. It means we are part of something larger. It means that the universe is not empty. It means that when we look up into the sky and wonder if anyone is looking back, the answer might be, somewhere, yes. The question of what we are gets harder with the Twin, not easier, because if life is common, then humans are less special. But if intelligence is rare, then humans might still be part of a small club. We do not yet know whether we are common or rare. We do not yet know whether our kind of mind emerges easily or only under extraordinary circumstances. The twin cannot answer that question directly. Microbes on the twin, if any, would not tell us whether minds are rare. For that, we would need to find life that thinks. That is a different hunt, and it is much harder. Atmospheric signatures can reveal chemistry. They cannot reveal thought, but the twin starts the conversation. It tells us that biology is happening somewhere other than here, and that, by itself, is enough to change the tone of every future discussion about our place. We are no longer speculating about whether the universe can produce life. We are asking what the life we found is like. That shift is permanent. That shift cannot be undone. And it began with one faint signal, in one night of data, from one small telescope staring across 120 light-years of empty space at one small planet that turned out to have a sky. Close your eyes for a moment. Picture the twin again. A small, rocky world, about the size of Earth, orbiting a dim red star, one face always hot, one face always cold. Between them, a ring of twilight where the wind never stops blowing and the star never moves. A thick atmosphere full of strange chemistry, possibly oceans of liquid water, possibly clouds of sulfur, possibly, just possibly, the breath of something alive. Now open your eyes and remember where you are. On Earth, under a yellow sun, in a blue sky that changes color every morning and every evening, on solid ground that does not burn or freeze, in an atmosphere you can breathe without dying. Everything you know, everything you have ever experienced, everything every human who has ever lived has ever experienced, has happened under this one sky, in this one gravity, on this one world. The twin is a reminder that our way is not the only way. Another planet, in another system, around another star, is doing things differently. Its surface is not like ours. Its weather is not like ours. Its sun is not like ours. And yet, somehow, it has kept an atmosphere. And in that atmosphere, chemistry is doing things that, here on Earth, only living things do. We may never visit the twin. We may never send a probe that arrives in any human timescale. We may never receive a message from it, or send one that it hears. Our entire knowledge of this distant world will, for the foreseeable future, come from the faint light it sends out in the moments when it crosses in front of its star. And yet, knowing the twin exists changes things. The next time you look up at the night sky, one of those points of light is the star the twin orbits. You cannot pick it out with your eyes. It is too dim, too far, but it is up there, and around it, at this very moment, wind is blowing across an orange-tinted landscape. A red star is hanging motionless on a horizon, and the atmosphere is slowly, steadily churning through whatever chemistry it churns through. Something is happening there, right now, as you listen to this. That is a strange feeling. It is the feeling of being, for the first time in the history of your species, not alone in your planetary activity. Somewhere out there, another planet is doing planet things, and we can see just enough of it to know. If the follow-up observations confirm the hints, if the dimethyl sulfide holds up, if the methane keeps replenishing, if the water vapor firms into surface oceans, then the next decade will bring an announcement that will be remembered for the rest of human history. You might live to hear it. You might be hearing its prelude right now. If the observations disappoint, if the signals dissolve into noise, then the twin will still have been one of the most important exoplanets ever studied. It will have taught scientists how to do this work. It will have forced new models and new instruments. It will have raised the bar for what counts as evidence. And the hunt will continue on other worlds, with other stars, until one of them finally gives up the answer humanity has been chasing for millennia. Either way, the twin has already done something no other exoplanet has done before. It has made us lean forward. And when a species leans forward, something always comes next.